Ever wonder why your electricity bill might be higher than you expect? Even if you're mindful of your usage, or why industrial facilities pay close attention to something called power factor. Today we're demystifying one of the most important concepts in AC electricity, power factor. Let's start with a simple analogy. Imagine you order a pint of your favorite beer. The actual liquid beer that quenches your thirst, that's what we call real power. That is the power that actually does its useful work, typically measured in watts or kilowatts. Next, we have the foam on top. It takes up space in the glass, but doesn't quench your thirst. That's our reactive power. It's power that builds up magnetic or electric fields, but performs no direct work. We measure in volt amperes reactive. Then, we also have apparent power, which is the entire glass, both beer and foam. That's your apparent power. It's the total power supplied by the electrical company, measured in volt amperes or kilovolt amperes. In an AC circuit, the relationship between these three types of power is not simple addition. It's a vector sum because the reactive power acts 90 degrees out of phase with real power. We visualize this using the power triangle. This relationship is governed by the Pythagorean theorem. Apparent power squared is equal to real power squared plus reactive power squared. The power factor is mathematically defined as the ratio of real power to total apparent power. Think of the power factor as a system's efficiency score. Since the apparent power is always the hypotenuse, and thus the largest value, the power factor will always be between 0 and 1. There's a second equally important mathematical definition of power factor in AC circuits. The real power is generated only when the voltage and current are in phase, meaning they peak and cross zero at the same time. When inductive or capacitive loads introduce reactive power, they cause the current waveform to be out of phase with the voltage waveform by an angle. Because the power factor is the ratio of the adjacent side to the hypotenuse on the right triangle, it is also equal to the cosine of the phase angle. If theta 0 degrees cos 0 degrees equals 1, the system is 100% efficient. If theta 90 degrees and cos 90 degrees equals 0, the power is purely reactive and no useful work is done. For a given load, the current is inversely proportional to the power factor. A low power factor means higher current. To avoid this, engineers use the power factor correction by strategically adding capacitors to balance the inductive reactive power, driving the phase angle closer to 0 and the power factor closer to 1.